Hello, Science Flow learners. Have you ever wondered why an apple falls from a tree, why the moon travels around Earth, or how a rocket can launch into space? More than 300 years ago, a scientist named Isaac Newton asked questions like these. Newton developed three important laws that helped explain how forces affect motion. He also used mathematics to explain gravity and the movement of planets. Today, we will explore the apple story, gravity, and Newton's three laws of motion. Our big question is, how did Newton explain why things move? Let's begin. Isaac Newton was an English scientist and mathematician who studied the natural world. He was interested in many different subjects. He investigated motion and forces. He studied gravity and the movement of planets. He also explored light by passing white light through a prism and observing the colors of the rainbow. Newton did not simply memorize facts. He asked questions such as, why do objects move? Why do they stop? Why do planets stay in orbit? And what rules connect motion on Earth with motion in space? His curiosity helped him develop ideas that changed science. What questions do you think Newton asked when he observed the world around him? Newton's discoveries did not happen in one sudden moment. He carefully observed nature, asked questions, made calculations, and revised his ideas. During the 1660s, Newton spent time at his family home in Woolsthorpe, England. Away from the university, he had time to think deeply about mathematics, light, motion, and gravity. His scientific process followed several important steps. First, observe. Next, ask a question. Then, calculate and investigate. After that, revise the idea. Finally, explain the evidence. One observation can inspire a question, but scientists need repeated observations, calculations, and evidence before they can develop a strong explanation. Why do you think one observation is usually not enough? You may have heard a famous story about Newton and an apple. According to the popular myth, an apple hit Newton on the head, and he instantly discovered gravity. But that is not the full scientific story. Seeing an apple fall may have inspired Newton to ask an important question. However, people already knew that objects fell toward the ground. Newton's achievement was not discovering that things fall. He worked to explain why they fall and whether the same force could also affect the moon and planets. His explanation required years of mathematics, investigation, discussion, and revision. The apple may have started a question, but it did not create the complete theory in one moment. That is the difference between a memorable story and real scientific work. Newton began thinking about two very different looking motions. An apple falls downward toward Earth. The moon, however, travels around Earth instead of falling straight to the ground. Newton wondered, could the same force affect both the apple and the moon? Gravity pulls the apple toward Earth. Gravity also pulls the moon toward Earth. But the moon already has forward motion. As gravity continuously pulls it inward, the moon's direction keeps changing. Instead of falling straight down, it keeps falling around Earth. This is why we can describe an orbit as a continuous fall around another object. So, if gravity pulls the moon toward Earth, why does it not crash straight down? Because its forward motion and Earth's gravitational pull work together to create an orbit. Newton's ideas about motion and gravity developed over many years. In the 1660s, he began forming early ideas about forces, motion, and gravity. In 1684, he returned to the problem of planetary motion and began organizing his mathematical explanations. Then, in 1687, Newton published his famous book, Principia. Inside Principia, Newton presented three laws of motion. He also explained universal gravitation and showed how forces could describe motion both on Earth and in space. It is important to remember that Newton's three laws of motion are not three laws of gravity. The laws of motion explain how forces change motion. Universal gravitation explains how objects with mass attract one another. Now, let's investigate each of Newton's three laws. Newton's first law is also called the law of inertia. It tells us that objects resist changes in motion. An object at rest stays at rest unless an unbalanced force acts on it. For example, a soccer ball remains still until someone kicks it. An object in motion continues moving in a straight line at a constant speed unless an unbalanced force changes its motion. A skateboard continues rolling until friction slows it down. We also experience inertia inside a vehicle. When a car or bus stops suddenly, your body continues moving forward for a moment because it was already in motion. A seat belt then provides the force that safely stops your body. Why do passengers move forward when a vehicle suddenly stops? The answer is inertia. Let's observe inertia with a quick experiment. You will need a plastic cup, an index card, and a coin. First, place the index card across the top of the cup. Next, place the coin in the center of the card. Now predict what will happen when you flick the card sideways quickly. Keep your fingers clear, and quickly flick the card away. The card moves sideways, but the coin tends to remain in its original position because of inertia. When the card is no longer underneath it, gravity pulls the coin straight down into the cup. Two ideas work together in this experiment. Inertia causes the coin to resist sideways motion, and gravity pulls it downward. Why does the coin fall into the cup instead of moving far sideways? Newton's second law connects force, mass, and acceleration. The relationship can be written as net force equals mass times acceleration. A stronger net force produces more acceleration. For example, when you push a shopping cart harder, its speed changes more quickly. Mass also affects acceleration. When the same force is applied, an object with more mass accelerates less. Think about an empty shopping cart and a full shopping cart. The empty cart has less mass, so it is easier to accelerate. The full cart has more mass, so it requires a greater force to produce the same acceleration. This means that acceleration increases when force increases, but decreases when mass increases. Why is an empty shopping cart easier to push than a heavily loaded one? Now let's investigate Newton's second law with two toy cars. Car A is light. Car B has extra coins or blocks attached to it, so it has more mass. Place both cars at the same starting line. Then give them similar pushes and observe how their motion changes. Which car will accelerate more? The lighter car will usually accelerate more because it has less mass. The heavier car requires more force to produce the same acceleration. Repeat the investigation several times and compare the results. However, there is one challenge. It can be difficult to give exactly the same push with your hand every time. How could we make the test fairer? We could use the same ramp, the same stretched rubber band, or another launcher that applies a more consistent force. Newton's third law explains interactions between objects. When one object pushes or pulls another object, the second object pushes or pulls back with an equal force in the opposite direction. These forces are equal in size, opposite in direction, and act on different objects. When you jump, your feet push the ground downward. The ground pushes you upward. When a swimmer pushes water backward, the water pushes the swimmer forward. A balloon or rocket pushes air or exhaust gases backward. The gases push the balloon or rocket forward. The two forces do not cancel each other because they act on different objects. One force acts on the air, water, or ground. The other force acts on the swimmer, jumper, or rocket. This pair of forces is called an action-reaction pair. Newton also developed the law of universal gravitation. This law says that every object with mass attracts every other object with mass. You pull on Earth, and Earth pulls on you. The gravitational forces are equal in size, but their effects are very different. Because Earth has an enormous mass, its acceleration is far too small for us to notice. Your much smaller mass means Earth's pull produces a noticeable acceleration in you. The strength of gravity depends mainly on mass and distance. More mass creates a stronger gravitational attraction. Greater distance creates a weaker gravitational attraction. The Sun has an enormous mass, so its gravity helps keep the planets in orbit. Earth's gravity keeps the Moon in orbit and pulls objects toward the ground. Gravity truly acts throughout the universe. A rocket launch is a great example of Newton's laws working together. According to the first law, the rocket remains at rest until an unbalanced force acts on it. The engines create thrust. According to the second law, the rocket accelerates when the upward net force acts on its mass. More thrust creates more acceleration, while greater mass makes acceleration more difficult. According to the third law, the rocket pushes hot exhaust gases downward. The gases push the rocket upward with an equal and opposite force. At the same time, gravity pulls the rocket downward. When the upward thrust becomes greater than the downward forces, the net force points upward. The rocket then accelerates into the sky. All three laws, together with gravity, help explain the launch. Let's review what we learned. Newton may have been inspired by seeing an apple fall, but his discoveries required years of observation, mathematics, and evidence. Newton's first law explains inertia. Objects resist changes in motion. Newton's second law connects net force, mass, and acceleration. Newton's third law explains equal and opposite forces acting on different objects. Newton's law of universal gravitation explains how all objects with mass attract one another. So, how did Newton explain why things move? He used scientific observation and mathematics to develop laws that connect force, mass, acceleration, motion, and gravity. Great work, Science Flow learners. Please remember to like, share, and subscribe. See you in the next Flow Space 101 Science Flow lesson.